Thank you, ma'am. Hello and welcome back to the very last session of the day, titled Application of GIS in Natural Resources Planning and Management, presented by Dr. Vinay K. Pandey, Professor Soil and Water Engineering and Dean, College of Agriculture and Research Station IGKV and College of Horticulture, Dhamtadi. He has completed his bachelor's in agriculture engineering from College of Agriculture Engineering, Jabalpur in the year 1963 and master's from the College of Agriculture Engineering and Technology, Udaipur. Later on, he earned his PhD from Indian Institute of Technology, Kharagpur. He started his career as research associate from IIM Ahmedabad, then joined IGKV Raipur. He served there at different key positions, including the head of department. He has a vast experience of more than 27 years in the area of agriculture engineering. He has guided almost 26 research scholars, including masters and bachelors. He was a founder dean of College of Agriculture Engineering and Technology, Mungeli, which was also the first agriculture engineering college in Chhattisgarh under IGKV. Few of his prominent works include development of farm pond, application of remote sensing technologies in watershed modeling, design and development of manually operate low lift irrigation pump, design of low cost poly houses, and many more. He has published more than 65 research papers in different international and national journals and conferences, and also visited many countries like USA, Germany, Thailand for different academic purposes. He is also a member of different prestigious societies and associations and recipient of Commendation Medal by ISAE, Outstanding Engineer Awards by Institution of Engineers, Rashtriya Ratna Award 2001, Krishi Ratna Award 2011, and many more. Sir, we are truly honored to have you here for this session and request you to start the session. Hello, Vinay, sir.
Yes, sir, definitely.
Okay. So, first of all, I'm very much thankful. First of all, not thankful, but before thanking, I feel very much sorry that due to some thing which was beyond our control, we are delayed by more than 30 minutes. So I'm thankful to the organizing team for who have given me an opportunity to present this one. Before the learned participants, I'm sure some of maybe very senior person, students must be there, some young scientists must be there. So for the very senior people, I excuse for anything if goes a little departure from the subject. But for the students and youngsters, I'm sure they will bear with me. So the topic of my today presentation is application of remote sensing and GIS in watershed planning and management. So watershed, as from the word there is something related to water. Since about when this watershed word generated, at that time watershed means something working on the land with specific reference to management of soil and water. But because this technique, this theme is basically for the rural development, for the farmers, for the villagers. So slowly and slowly question come, if there is one person in the village who don't have land, so can we not think something for his development? So we added the people who are landless in the village, they don't know, they don't have cultivated land with them. Then slowly and slowly people, plan for the people who don't have land, who are not interested in cultivation, but at village level they can do something. So all developmental activities slowly and slowly come under the umbrella of watershed, with special reference to agriculture and management of soil and water resources. So nowadays, watershed become a theory of total development. So anything, any concept, any work, we go in the villages, we work for the land related to management and conservation of soil and water resources. It comes under the watershed management. But still, the basic theme behind watershed management is the conservation and management of soil, water, and vegetation resources of that particular area. Now, uh, let us come to the its technical definition of watershed. As per technical definition is concerned, the watershed is the land area which is draining to a common outlet. Why a scientist and engineers define this definition? Because we have to select a unit, a certain unit for its development, and that unit should have some technical concept of its own. So this way, watershed becomes a topographical unit, a part of land, a part of some village, district, block, forest that drains to a common outlet. Drains to a common outlet means whatever rainfall is there during rainy season, it should come or it should discharge through a common outlet, common point, and that common point is known as the outlet for the watershed. So basic theme, pinpointed theme for management of watershed is managing the water and the soil which is being eroded during the rainy season. And of course, vegetation and agriculture too. So, for management of watershed, first we should have a look upon the runoff and sediment yield. Then its hydrology, then socio-economic status, crops and cropping pattern, soil type, present land use, cultivation practices, habitation, settlement. So these are the some of the information that we need for the it's better planning for management. And at the end of the whole process, we the requirement of that the farmers and the people of that area. So we need a modern tools and techniques for the better planning of watershed. So if we see as a whole, so first we have to plan the things, then we have to execute the measures, then we have to manage the measures for better conservation of soil and water resources in general, and the overall development of the people who are residing there, maybe farmers, maybe laborers, or whatever, which category belongs to that particular land. So initially, about I know personally before 30 years back, for watershed planning, we were making a contour survey. Then after contour map, then we are generating soil map, then revenue map, present land use map, and are these 4-5 maps we were superimposing the same scale to each other. Then we were developing a developmental plan. According to developmental plan, all engineering and agronomical measures were planned. Their engineering design were established. Their socio-economic conditions were analyzed. Then finally we were executing these structures, engineering structures on the ground. Now, slowly and slowly, on development of the technologies and to be the concept to execute the things in very less time with high quality of efficiency. and accuracy. We could get the things like remote sensing and GIS. So when you use the remote sensing, when we use the GIS technology, we can go for the very high level accuracy with very efficient way and with minimum time. Now, today I'll not go on explaining the physics and theory of remote sensing. I'm not going to tell you much about the physics and its theory of GIS. Most of most of the students, young scientists, and all senior people, they are well aware with the remote sensing concept, its definition, its introduction. Well, I suppose. Now, today we'll discuss only application part of these tools and techniques for the watershed planning and its management. So, as a watershed, as you are able to see in the slide, it is an example of a topography which is draining to a common outlet. An outlet is nothing, is the lowest part of a topography. So whatever water is coming during rainy season from this ridge area, it is draining to a common outlet to the channel, and from there it goes out. Now we have to execute the measure from upper side to the lower side, because if you are going to execute the measures from lower side to upper side, technically this will be wrong. So at whether watershed belongs to 10 hectare or 10,000 hectare, ultimately this is the unit of our management. Then after planning and our designing of our engineering structure, we have to place the structure in sequential way. As I told you, there are two kind of structure. One are agronomical, another engineering. Being a civil engineer, you must be doing engineering structure. Nothing. Stop dam, percolation tank, gabion structures, contour bund, grass waterway, farm pond, small dam. Are that so? These are all engineering structures. We go for execute for conservation of water and soil. Then, as per economical structures are concerned, these are, say, maybe crop selection of crop and cropping pattern, plantation, boundary plantation, some soil erosion preventive plantation with respect to techniques. So we cannot say that only we go for the engineering structure. Overall, for the better conservation of the natural resources, we have to make a combination of engineering as well as agronomical measures. So, watershed planning, as already stated, it involves management of light, water, energy, vegetation resources with relevant scientific input appropriate to the socio-economic background for a pragmatic development. Ideally, it involves effective soil and water conservation measures, generating less green cover such that load-free runoff is generated. Means within the runoff, there should not be much load of soil particles. So this way, a holistic development of a certain region is thought of. So now we need certain information, basic information for better management of your watershed. So first, as we started with the remote sensing application, so we say remote sensing data. It is in FCC form or digital form based on present availability. Then collateral data, meteorological data, soil data, crop and cropping pattern, vegetation cover, topographical features, present land use, groundwater, socioeconomic. So this way we need a series of data for its better planning. Then remote sensing, as I told you, we are not going to discuss the it's a theory and introduction of its physics of remote sensing IGS. Only with the basic definition, will switch to the its application part, assuming that our participants, they are all not may not be fully familiar with and tools. Then if you discuss something about its role, then it's a remote sensing data both from aerial and platform offers a faster, efficient and reliable data acquisition technique. Remote sensing data have unique character. It is the same database which is utilized by various thematic specialists, and hence it is of multidisciplinary utility. In case of watershed management, the information is needed on soil, distribution of rainfall, runoff, potentialities, land use, environment, and lot of such natural things are required. And most of these information can be extracted from the same database. Then remotely sensed images constitute an integrated view of the landscape with all features. Then remote sensing derived information can be merged into the integrated with conventional database using suitable software. Of course, some of the data we can collect from the ground, from the villages, and that information can very well merged or inter-transfer within the data available from the remote sensing images, and the whatever data we are collecting from the ground truth. Then these diverse data system can serve the input and can be converted into the consistent map format, and this can be done in very efficient and very time economy manner. Then using suitable software, specific integration and analysis of these data can be performed with a very short time period to derive useful output in the form of maps and statistical data. Then GIS serves as an efficient system for compilation of these information and presentation of these information in terms of maps, in terms of tables, in terms of graphs, etc. So these are the two techniques. If you apply these techniques in watershed management, watershed planning, so we can get the things in very timely and very efficient manner, and that too with high level of accuracy. So this is initially I showed you picture of a watershed, how watershed looks. How it may be 5 hectare, 10 hectare, 10 hectare. It does hardly matter. But broad. What is a technical concept that it should drain at a common outlet. So this is in front of you that this is 3D view of a digital elevation model, and digital elevation model is nothing but it's outcome of generated through the contour map using GIS. So if you develop a contour manually, or we develop a contour digitally, we can transfer this database to the GIS platform, and we can get a digital elevation model. So you see, this is the lowest point in the content. You are having the reduced levels. So this is the lowest. This is an example. Of course, this is an example of watershed. So this is the lowest point from where all corner of ridges water collects and drain at this point. So it has one outlet. Different color shows the different kind of topographic signatures and features. Then this is another view of same map. These are the drainage lines. So in a watershed, this is outlet. This is the watershed boundary, and these are the drainage lines. Drainage lines are nothing but the pathway through whatever water is falling on the surrounded area. It drains through these small channels towards the outlet. So after taking selecting a watershed, what information that we need to collect, analyze for its efficient planning. So first thing is the location, it's longitude latitude wise. Then what is the average rainfall of that particular area, what is the mean and maximum temperature of that particular area, what is the relative humidity. So in this way, whole climatic information we need to collect. Then topographic map, of course, that is topo sheet we need to collect. Then soil map we need to collect, because it's not possible for each and every man, for each individual agency, for each individual organization to get the information of all kind. So what we do, we collect the soil information from Survey of India, from Soil Survey of India. We collect the topo sheet from Survey of India. We collect some basic information from the district level and institution level. So this way, to generate different layers, we need to collect different kind of information. So now see how these individual information are slowly and slowly going to single platform, how they join and develop a developmental plan using remote sensing and GIS technique. So this is the soil map, right? So we collected the soil map or soil information from soil. If the area is big, then we have to collect from the expert agency. If our area is small, no problem. We can take soil samples. We can analyze in the laboratory, and after analyzing in the laboratory, we can prepare ourselves a map. So this is up to our capacity and the information and the resources that we have with us, with our organization. So this is the soil map of this watershed area, and you see there are 1, 2, 3, 4 kind of soils are there. Sandy loam is there, sandy clay loam is there, and loomy sand is there, clay loam is there, and you see the different percentage of that soil is there. So the whole area is dominated by sandy loam soil, and this map is generated using GIS platform, ArcGIS. So what we do to generate this layer, we collect a we collected a soil map from Soil Survey of India. We digitize, and after digitization, this soil map is generated. Then this is another, of course, this is soil map. We call it soil series map. So soil series map, you see, these are Amra, Dumka, Hasla, Salka. These are the local name of the soil series. Those names are, initiated by the villagers, by those people, some years back. So soils, this is the soil series map, and all series belongs to local nomenclature. So that the same area having 4 soil classes, but 13 soil series. Then this is the soil class map. You must be knowing the soil classes. Total we have 8 soil class, and the classification of soil is done based on the its property and its suitability for that particular soil. So here we get 1, 2, 3, 4, 5, 6 soil soil classes. So class second, we have this much area. Class third, we have 30.69%. Class fourth, class sixth, and class eighth. So class eighth, we have the 0.74% area. Means most of the area is suitable for the cultivation, or you may say it is the it is having good soil. and class A, which is almost barren land. It's not suitable for the cultivation. So that area in the watershed is, percent of that area in the watershed is very less. So after doing this exercise, we have to analyze the soil properties: bulk density, available water holding capacity, saturated hydraulic conductivity, sand silt clay percentage, K factor, porosity, pH, etc. So now for in-depth study, in-depth planning, we have to analyze the soil sample, and all these property needs to be analyzed in the laboratory. Then another part is crop and vegetation. We have to visit the area. What kind of crops are being grown by the farmers? What kind of natural vegetation is there in the watershed area? So we need to record these information also, because this all information is going to analyze, and this will affect each and every information will affect the total generation of runoff and silt load at the outlet. Then see, this is the contour map. Of course, the lowest elevation is 200 and the highest elevation is 300. And this is the outlet of the watershed. So this is the contour map. And as you have seen the 3D first picture, is an outcome of this one contour map of this watershed. Then again, this is another view of digital elevation model, and these layers are generated using remote sensing and GIS technology only. So this way we can see that how for making development plan. We proceed with the digital data, remote sensing data. So we take there are number of softwares, number of techniques. So for example, if we correct the multispectral if we go for the multispectral classification, so there are two: supervised and unsupervised. If you go to the theory of supervised, it will take another, I think, more than a week to discuss supervised classification. If you go for unsupervised, it will take more than 1 week for go. So we are not going to that much detail. Only the idea is how to take a digital data, go for the classification. So either supervised or unsupervised or in combination of both, we take the images for the classification. Then we go for the training stages through which statistical ways some classifier are used. Then classification stage, their maximum likelihood classifier, we call it MLC, based on the estimate and Gaussian probability. So there are a number of basic theories and mathematical models on which this classification stages are depend. So using these software and techniques, we go for the classification of the image, and then finally we go for the accuracy assessment, right? So classification is nothing but understanding or depicting the signature, topographic signature, what are there on the ground. So this way, remote sensing technology is very accurate, is very fast. So this is the one example diagram, flow chart, through which how we can step by step we move up to the classification. So taking right from starting from data, we get the final report and the maps of image classification. Then, so this is the outcome after classification of images. So when we go for the very accurate planning, we have to do whole exercise for the two time period. One for the calibration and another for the validation, because there are quite possibility of human error, or n number of chances are there where there may be slight or more departure from the reality on the ground. So we take the data, 1 year data for the calibration and another year data for its validation. So this is land cover classification map for the calibration year. Calibration year may be one. It's not whole year. It may be one pass. You must be knowing that how satellite data is being recorded from our country or from the world. There is certain period when satellite moves. It takes the data. That data comes to ground station. From ground station, after certain rectification, it comes. So it's another process. We are not going to discuss about the satellite technology. Only our idea today is just to application of that technology in our watershed management, right? So you see, after putting these digital images into the image classification software, see, we have got such a layer, and these layer shows different signatures: the water body, lowland paddy, low upland paddy, fallow land, upland, settlement, mixed forest, waste, etc. Right. So after getting this classification, again we go to the ground for the random checking whether the whatever information we are getting is correct or there is some departure. So based on ground truth procedure, we can correct this image. Then for another image, for validation period, we do same exercise, and after doing this exercise, we go for generating a table. It is called the maximum likelihood report. So through this report, we can get information: water body, what are number of pixels, what is the area, how much percent image belongs to water body. So this information for the calibration year and another information for the validation year. So if you see this data area, at least, so this way we can say that whole watershed of say 150 hectare, 270 200 and 1000 hectare, 270.94 hectare belongs to the water body. So this way we can get the information about how much lowland paddy is there, how much upland paddy is there, how much fallow land is there, how much villages and city, roads are there, mixed forest is there, wasteland. So this way, whatever information is there on the ground, we can get after analysis of, we can get a precise record of that information on our this one to software, satellite images. Now another layer is ordering. Stream order is nothing but again it's an outcome of digital elevation model. So as I told you, these are the lines, streams which shows from which direction to which direction water is flowing during the monsoon period towards outlet. So because water and soil are the key factor, so we have to have an account of each gram of soil, each drop of water which is moving throughout the watershed. Then only we can make a perfect plan for its management. So there are some ordering system in the streams. So based on their orders, we go for the divisioning of the watershed, because this whole area is 5,000 hectare. So for anything which is bigger in size, which is larger in area, it's very difficult to manage and plan at once. Right? So for this, we have the provision, or we have the idea, so that whole watershed, say for it's 1,000 hectare, we can make a division of sub watershed, small units, so that it would be better to plan, it would be better to execute, and it would be helpful for this. It's a post So this way you see, we have got 8 sub-watershed, 1, 2, 3, 4, 5, 6, 8 different colors. And if you see the movement of streams, layout of streams, it is in very clear-cut defined that water moves from this direction and join here. Water moves in this direction and join here. Water moves in this direction and join. And whole stream, the water from the whole stream ultimately is going to the common point, that is a major outlet of the watershed. So instead of one whole watershed, we have now generated 8 small units. So based on our manpower, based on our facility, based on our resources, based on our budget, financial allocation, we can go for the execution either unit wise or at once the whole unit. Now we need very precise and technical data for each and every sub-watershed. So data means total land, how much average slope is there, what is the Manning's coefficient, which is showing the roughness, texture or properties of the soil, and its overland flow, its elevation, its the slope. So all these technical information, technical attribute we need to know for each watershed. So you see, after division of main watershed into 8 sub-watershed, sub-watershed wise, we are generating these information, and these information are generated using remote sensing and GIS tools. Then sub-watershed wise land use and soil distribution. Of course, we need to have a soil map. So these are the soil information, land use cover information of whole watershed. Then question comes, we are showing stream order. Now we are speaking about the soil. How within same map? So it is generated because soil layer, contour layer, land use layer, revenue layer, all these layers we generate and superimpose in the same scale. So when we superimpose these layers in the same scale using certain software, so whatever information is generated, it is sector wise, it is sub-watershed wise. So now we can say, suppose, for example, watershed number 5. So for 5, area will have separately, we have the property of soil separately, we have the land use pattern separately, we'll have in the vegetation information separately, we can have the water information separately. So this way, and this separation is for nothing, it's just for the precise planning. So this way, watershed wise, then sub watershed wise channel attributes. Channel, there may be main channel or there may be tributary channel through which water flows during the monsoon period. So we have to have the all technical information about the channels also, because we have to keep an account, keep an observation of each and every drop of water. That's why the information is required. Now, uh, it's not the end. It's not the end. Ultimately, we have to get the plan very precise in very timely manner. So one manage GIS, another manage remote sensing. Then there is a need of third man. Third man is a hydrological model, and we need fourth man. We are the fourth man. We are always intervening. We are going to the ground. We are doing ground truth, and we are keeping the eye on working of these three gentlemen. So we got the special information through remote sensing GIS, dam, topographical features, about soil property, about land use, and some of the database like meteorological data and other information that we collected from the ground, that is there. So this is in the form of images, digital images, and this is in the form of tables. Then another gentleman gives special distributed this one. So this is the information that we collected from using GIS, the remote sensing, and manual data collection. Then another third man is hydrological model. So now we have to join to each other, because ultimately we need a result. We need some output. So to get an output, we do some interface with hydrological model and whatever data we are getting. So of course there are softwares, there are models, there are provisions. Only why I'm telling this thing in detail, so that at least students and young scientists who are just involved themselves in doing this technique, they can. And I'm sure that all senior people, they are well aware of all these things. But it is useful basically for the our young engineers, young scientists, and students. So this way, whatever information we could generate using remote sensing and GIS, now we are putting now we are interfacing with these hydrological model and another GIS model, and through interfacing we can generate output. So output will again come in terms of layers, in terms of graphics, in terms of tables. So whatever data we collected, this way we can get the output of this database, and this output is going to be used for the designing the structure and for efficient planning of that particular watershed. Again, I'll tell you, whether watershed is 5 hectare, 10 hectare, or 10,000 hectare, concept is same. If you are using this technique, certainly your accuracy and efficiency will be very high. Then one term I use, hydrological model. So model having its own theory, its own. So how different hydrologic balancing components are there and how they are simulated within the model. So I think this is nothing but it's just hydrological cycle. And nowadays, even the when our kids goes to the first class KG1, they are well aware with the hydrological cycle, how water is coming, how vegetation is there, how water falls on the ground. Some it creates as a runoff, some goes as a lateral flow, some goes into the deep layers, and some goes as a percolation, some comes as a return flow. So through different layers of the aquifer below the ground. So looking and part of them, part of this water is going again as evaporation and evapotranspiration to the sky. So this way whole hydrological cycle is working, and within this hydrological cycle, these are the different components on which hydrological model is working for giving the value, how much runoff we are going to get from this watershed, how much sediment load we are going to get from this watershed, how much carbon matter we are going to out of at the outlets. So based on that result, we can plan the conservation measures. So one prevalent equation, that is a water balance equation of the model that is working inside the based on which whole water balance is calculated. So I assume that our young participants, mostly students who are working in the area of water resource engineering, water management, they must be aware of this water balance equation. So I'm not going to go in detail of each and every component, but by and large, soil water contained in is soil water, precipitation, surface runoff, evapotranspiration, evaporation, percolation. These are the sum of water balance component. Those are there in the equation. They are working with the when we simulate the model, hydrological model using GIS and remote sensing interface. Then after doing this exercise, we have to go for the statistical analysis. Statistical analysis for the calibration period and statistical analysis for the validation period, so that after this exercise we can get that what is the difference between our observed data and simulated data. So simulation we are doing using remote sensing, GIS database and observed database. And collected database. Where is observed database? Where is observed database? Observed data means on the ground, different respective departments, they are putting their instrumentation for regarding of outflow, runoff value. So that value we collect from those departments or from those stations, and that value is then compared with the simulated data, so that we can get how much departure or how our efficient simulation is there when we compare our real ground data. So this is that exercise, and this exercise we perform for the validation period as well as for the calibration period, for both the period. Then after doing this exercise, we can get a graphical representation of simulated data and validated data. So this is observed value, sediment value, and these are the simulated value. So this graph shows that whatever simulated values are there, they have very close relation with the observed value. So if this is the case, means whatever simulation we have done, it's almost perfect. And based on this result, based on this data, if we are planning any conservation structure of the watershed, certainly it will work very efficiently, very accurately. So this is the purpose of doing this exercise. So after sedimentation, we have to go for the similar exercise for the runoff also. If you go to the stations where the recording of runoff is there, recording of discharge data is there, we have to collect those data, maybe 20 years, maybe 10 years, maybe 50 years. And that data we have to keep in another track. And after simulation, we have to compare our data, simulated data with observed one. Then through these techniques, tools, softwares, we can compare the values between the observed and simulation. When we are sure that, of course, there is very strong good relation between observed data and simulated data. So based on those information, we can go for the further planning. And data is nothing. Data means after simulation also we are going to get two information about sediment at the outlet and about runoff at the outlet, because we have to conserve the runoff water and we have to conserve the soil. And once we conserve and manage the soil and water property in the watershed, so all management techniques will work perfectly, whether it is agriculture development or it's vegetation development. So, as I told you, water and soil are the key term in the watershed management, and the proper management, proper collection, proper information, proper validation, proper calibration of these two terms, we can go for the its perfect planning. So, average annual output of the model for the identification of critical subwatershed, it means 8 watershed we have collected, and for the all 8 watershed, we have simulated the value of runoff, we have simulated the value of sediment, we have the sediment, how much nitrate, nitrogen loss is there, organic N loss is there, soluble P loss is there, organic P loss is there. So these losses are observed value also, because we collect the sample at the outlet, we go to the laboratory, we analyze and make a table, make a register for observed value. Secondly, we take the value which we are getting through the simulation of the model. Then we go for the comparison. If the observed value and simulated value have the close relation, then we go for the simulated value, because we are going to have a plan for the coming 50 years. It's not for the 1 or 2 years. So planning for the 50 years should have very strong database and accurate database. So this is the idea about the recording the data of each subwatershed wise all information. Then similarly, Mm. Crop information, number of crops are there. We visit to the ground, we make a ground to survey how much, for which and how much acreage of that particular crop is there. Then what is the status of this crop in producing runoff? What is the status of this crop in developing, in producing the sediment yield? And all these parameters. So this way we have a relation with different crops, relation of different crops with the production of sediment yield and discharge of runoff. So this information we have to collect. So similarly, we can simulate in the model the effect of different tillage in sediment and runoff observation, at simulation of different tillage practices and yield of nitrate, nitrogen, soluble P, etc. So and organic, etc. So after getting all the information, runoff, sediment, organic matter, nitrate, nitrogen, P, soluble, maybe other than there may be another parameters also, there may be another information also, but as an example I have tried to convey you these values, through which way, through based on these values we can go for the perfect watershed planning. So this way we can say there is a big role of remote sensing and technology, remote sensing and GIS technology, for, and of course in combination with hydrological model for efficient and accurate planning of watershed. Then after doing this thing, we can put some 2-3 conclusions. The usefulness of remote sensing satellite data, obtaining high dynamic land use, land cover information on a spatial scale is highly useful. Then model stability to simulate number of different processes and its link with GIS interface have a great potential as a tool for predicting the sediment yield. Then similarly, if you go for the statistical calculation, then coefficient of determination, nice settling coefficient, and overall deviation. These are the some components that shows the accuracy of our process that is there. Then average rate of annual sediment yield from that particular that case study which I am presenting is 1.45 to 2.4 ton per hectare per year. Then out of 8 watershed, after doing the exercise, we declared that which number of watershed is the most severe for the treatment, because out of 8 There's no equal distribution of runoff. There's no equal distribution of sediment yield. There's no equal distribution of discharge of NPK and all these chemical components, organic components. Always there is a variation of in all components. So this way we can predict that which number of watershed having the highest severity, means most maximum value of sediment load discharge, maximum value of runoff discharge. So this information give us that first we have to go for treatment of watershed number 6 because that is more severe. So this exercise give an idea that from which area we have to start our execution. It's not like this. Let us start from 1. Let us start from 8. No, it's not like this. This table shows, this information shows that which area need immediate action for its execution. So this way we can make a prioritization of a scheme based on application of remote sensing and this model for the ground reality, and the model used successfully for identify critical subwatershed for developing best management practices. Management practices may be a number, but we have to select which is the best in view of topographic situation, land situation, soil situation, cropping situation, and socioeconomic condition of that particular area. So this was the in brief about its application of this technology in watershed management. Now I would like to show you some pictures that after doing this huge high-tech mathematical technique, what is going there in the ground, for which we are discussing since last 40-50 minutes. So after getting this information, we go for the planning of different engineering and agronomical measures, structures. So after seeing these pictures, you will understand that yes, these are the structures, these are the measures, and how they looks on the ground. And if they are there on the ground, how runoff is controlled, how soil loss is controlled, how carbon matter is controlled. And if these are the control, how agriculture production can be improved, how land itself can be improved, how cropping pattern can be changed, how water storage structure can be enhanced, how groundwater can be recharged better way. So within few minutes, I will sum up. So these are some engineering and economical structures, especially for the watershed management. And normally we know the dams, we know the river, we know the aqueducts, but these are some small structures. Those are specially designed for the watershed management. Gully plugging, contour bunding, gabion structures, percolation tank, check dams, cement plug, nala bunding, recharge shaft, dug wells, groundwater dams, subsurface dikes, and there may be another structures designed by the farmers, innovated by the even local peoples, named by even after local peoples. So they may be also there. So this is just view of say this is a part of watershed. These are the drain lines. How gully plugging is done. Small gully is there, so we are putting gully plug structure. It may be made of local boulder. It's not necessary that we are going to, in the watershed management, hardly we go for any big and any pakka structure. Mostly we go for we design the structures which are made of locally available materials, stones. Then other, of course, this is a stream. Water is coming this way. So how one barrier can be created so that during the monsoon, the running nature of water can be diverted into the walking nature, and any water which retain on a certain ground for the longer period, it will go deeper, percolate deeper, and recharge our ground strata. So at once there are 2-3 processes takes place. If we make a speed of runoff slow, then erosion will be controlled. Once erosion will be controlled, then top productive soil will retain where it is there. If speed of runoff is controlled, that water will get more opportunity time to stay in that particular area. Once it is there, then certainly our groundwater recharge will be more. Then there will another be a good thing that due to less erosion, enlargement of gully and creation of new gully will be reduced. So there are 3, 4, 5, 6 processes takes place at the same time during the monsoon period. Then this is the side view of design of spillway. Most of the civil engineering people, they are all we are involved in designing biggest pakka structure. So this is spillway, especially designed for for watershed management. Then cross section of this contour furrow. Contour furrow is nothing. It is designed for the slopy lands. Slopy lands. So we make a furrow on the contour itself. So whatever running water is coming from the upper side, it retains or it stops on the furrows for the longer period. So this way groundwater recharge and whatever vegetation is there around the contour, it grows. So after 1 and 2 rainy season, you will find that the one barren land, exposed land will be covered by slight vegetation. So this is structure designed for that one. Then cross section of PRT Puerto Rico terrace. Again, again, this is designed for the some slopy lands. This is the stone fencing wall. Of course, there may be a number of fencings we everybody see, but in the villages where stones, locally available stones are there, so especially this stone fencing wall design, its height, its width, its thickness, all parameters are technically designed based on the soil properties. So this structure is also useful for the watershed management. Grass waterway is nothing, it's just disposing the water safely in the onward direction. Say suppose we have created any cut, a small dam. So when the water comes out of west weir, then sometimes we forget it's going, let it go. No, if you are passing this west weir water, excess water through grass waterway, it will prevent the topsoil to be removed and the disposal will be very safe. It will not damage to the forward crop of the farmers. So this structure is also very much useful in the watershed management. Then loose stone terrace. Again, where stones are available, mostly in the hilly areas, we design a terrace. This structure made of loose stones, locally available stones. Then this is earthen embankment, of course, or the Pakka Dam. Every time we have seen lot of in lot of places, even in rural, number of government schemes are there where any cuts and dams are designed. But earthen dam, of course, where there is a some combination of available funds, topographic situation, available the earthen dam. This will serve our purpose. So this way, this small structure is designed for the watershed management. Then contourments, of course, where the slope is less than 6% in the cultivated field, is still where the slope of the cultivated fields are less than 6%, is still there possibility of erosion. Water can move. So if you go for the contour bunding, this way we can cut the slope. And once we are cutting the slope, certainly the nature of speed of runoff is reduced. So topsoil, erosion of topsoil will be prevented, and our whole field slowly within few years will be flatter. And certainly once topsoil is retained, this fertilizer is retained on the that field itself. So crop production, vegetation will improve. So this is the one of the structures designed for the cultivated land. Then diversion channels. This is required in the watershed area in the villages where we get excess water, whether it is during rainy season or in another season. So put the diversion channels to save moment of water and avoiding the damage of farmers' field, farmers' crop with excessive flow. Now, these are the some pictorial diagrams which are mostly used in the watershed planning, watershed management. So, as I told you, there are two kind of structure. One is engineering, another is agronomical. So, these are the engineering pakka structures. Agronomical structures, measures are nothing, just plantation, crops, and cropping pattern. All vegetative kind of measures comes under the agronomical measures. So these are the Nalaband. This is another any cut. So see this one gully is coming, and by putting this small structure, we can retain some water, we can retain some soil, so that further enlargement this gully is reduced, and after when the certain water is ponded there, it will recharge groundwater also. It will fill up. Sometimes there are cases in the villages, even once small structure is filled up with soil, people say, no, this is wrongly designed. No, it's not like this. The purpose of each and every structure is not to ponding the water only. First year, second monsoon, there may be pondage of water. But if after third monsoon, it is filled up with water or soil, it's silt up completely, even it serves its purpose. So in rural area, in the small scale, if any structures is a small structure is silt up fully, even its purpose is solved, because it has stopped the erosion of excessive soil and enlargement of dimensions of gully. Then you see this is a open this field, right? Even there is some drains are there, some ridges and furrows are there, because furrow need to be need to serve two purpose. Irrigation come down a channel, then in the ridges we have to grow certain crops which don't require that much amount of water. So this way, based on the cropping pattern and topography, we go for the designing ridge and furrow system. Then see, this is the hilly area. Here we put some contour furrow, then graded furrow, number of structures are there. See, this is the area how we creating so whatever runoff is coming during the rainy season, then here this is ponded for the longer period. On these bunds, we can grow some crops. Similarly, see, farmers are there is no any engineering structures, but still there is a change in the cropping pattern. If based on the slope, based on the topography, we are not advising to the farmers to take a certain crops, plow your field in a certain direction. Technically, this should be wrong. And in the longer term, either there may be excessive erosion or loss of topsoil. Ultimately, it will reduce the crop production and productivity. Then see another structures. This is another small structures, maybe nala, you may say manala band or maybe any cut. So how this is designed. So designing each and individual structure, all those data which we have already discussed few minutes back is required. Because at this point, how much runoff is coming, how much sediment load is coming, what is its catchment area. So all these data we already analyzed previously using remote sensing GIS softwares. Then based on those values, we are designing these structures. Then see, this is a Gabian structures. Gabian, we take a wire, just chain link wire, and within that, inside that wire, we put locally available boulders. And once this structure is fitted here, you'll see that excessive water is draining outside, but whatever soil, silt is coming, it is retained. And after 1 or 2 seasons, all pores are filled up with clay soil, and this structure will retain the water also and conserve the soil also. Of course, these are the some structures made in the nala, some local available nala, small rivers. See how side wall are created using these small locally available stones. There's no pakka structures. So idea is these are the some of the these are some of the structures small scale small design small value structures that serve the purpose of purpose of reducing the runoff and soil loss. Then you see in the forest area, if you don't assume that the structure, of course this is the structure locally available boulder structure is not there, then there is quite possibility of heavy runoff and heavy detachment of soil around these plants, and in within a short period this all vegetation may go. So within the forest area, even maybe the low dense forest, the small available material we can collect, the structure can be designed so that the flow of water, flow of runoff can be reduced and maximum soil can be retained where it falls. See, this is a totally wasteland. On the wasteland, we are putting some ditches for the plantation, and this a gully is there. So this gully is treated with the small boulder structures at different places, so that further enhancement of this gully can be reduced, and whatever depressions are there in due course of time, they will be filled with the soil. Another structures, boulder structures are there. They are in the forest land. So in the similar way, we can reduce the velocity of runoff water and retain the soil for its better growth of vegetation. We all seen in the different places. Some ponds are there. Normally, it is technically advised that in 1/10 part of your cultivation land, one should go for the small farm pond. So small farm, it's not randomly created. It's already designed based on our previous data. What should be its depth, its height, its berm, its inflow, its outflow, how much capacity, how much water, depending on the crop requirement we can use for the irrigation. So this is another structure basically used in the watershed area. See another picture. This a small nala is coming. So mesh wire structure is there. This mesh wire channeling wire is there, and locally available material is there. So we can retain some water and retain the valuable topsoil which is coming. So so that was the cases or photographs of forest land. This is the grass waterway I was telling about. This all cultivated land, but whatever excess water, even maybe during the rainy season is coming, it should safely be disposed to prevent the harm of farmers' crop from the excessive velocity of flowing water. This is the another structure. Some plantation is there, some crops are there, but still there is a small pond created for the storage of water and groundwater recharge. Similarly, there is another treatment. Some field bund is there, and farmer is advised to take some crops on the bund so that topsoil can be prevented from the detachment of soil through raindrops. Some another photograph in hilly area, some terraces has created, and on these terraces farmers take some crops. At the same time, some soil and water is retained, and this way we can recharge the availability of water. Forest land is also treated this way. This is the untreated gully. Certainly, if it is not treated, whether by the pakka structure or by the boulder structure, year by year, the size of this gully will be enlarged, and in due course of time, a good soil will flow away from this area. So this is an example of bad situation, and these are an example of treated situation of the watershed. So another way we can see this is not the cultivated land. This is but it's very slope is not much, so we can plant for the grass soap plantation. Then in between two row of plantation, one can go for vegetable and other this thing. So this way, such land can be planted based on total availability of runoff and soil loss and nutrient loss. We can plan for the mixed cropping pattern for the farmers. Of course, as usual, this is another pond in the slopey area. See, it is locally made by even by the farmers, and life-saving irrigation can be provided to the nearby crops. This is a very high slopey land. How gabion structure is created. There's no cement, no rods, nothing. Only based on available local boulders and wire mesh. This structure can be designed for a particular location. Then these are the series of structures, because one gully, one valley cannot be treated effectively using only one structure. So instead of using one structure, along the gully, we can put such a series of structure so that water and soil both can be retained in a certain, and once water and soil is retained, certainly vegetation will grow and vegetation will also be retained in that particular area. So this way I end my talk, and whatever I could produce within this short period. Again, I'm very much thankful for the organizers who have given me an opportunity to present this information. I'm sure even some of the participants, I'm sure that they must be having knowledge more than me. Of course, they can present the same thing in better way. So this is always there. There's no end of learning. So I always suppose that by presentation, by listening to others, or by presenting before others, all the time learn and improve ourselves. So with this, I again thanks, and I request if one or two questions or queries are there related to this, I feel happy to answer them.
Okay, thank you so much, sir, for the talk. Although we faced a lot of technical issues, but fortunately able to overcome it. Looking at the topic, it is something